Welcome to Trig Limits Day 4, evaluating limits numerically and trig limits. On the front page here, we're just going to talk a little bit about how to look at a table and deal with limits from that. One of the reasons I think that the AP really emphasizes this and that we try to emphasize it in mathematics education in general is when you're dealing with things in life, it's often that you don't have a formula. You often have a data set. You go out, you research something, you collect data, and then you make a formula from that. So it's very interesting and it's very important that you be able to look at information that's just a numeric form and try to make conclusions about it. So anyways, when we look at a data set here, and I ask find the limit as x approaches 2 from the left, I know I'm looking near 2. So when I evaluate the limit as x approaches 2 from the left, I'm going to find 2 in the table, find the numbers to the left of 2, and say, all right, as x comes at 2 from the left, y is approaching 3.999, y is approaching 4. I do not look at this at all when I am looking at the limits. So if I want to come at 2 from the right, I say, okay, this stuff is to the right at 2, 2.1, 2.01, 2.001. These are all going to 4. Therefore, the limit as x approaches 2 is 4. I didn't have to look up at all because these two both already equaled 4. And then, last but not least, when I come over to here, f of 2, well, that would be the function value. And the function value at 2 is right here, and that is also 4. One thing I can now say because of this table is not only does the limit exist, but it's a function that's continuous at 4, assuming that I know that these are continuous elsewhere. I know that this is continuous at 4 because the limit equals the function value. So down here, example 2, I'm looking at 5 from the left. There's a fire drill. Hold on. Sorry for the weird pause. We had a fire drill. Anyway, so here we go. We're in example 2. Same idea. Limit as x approaches negative 5 from the left. So 5 from the left, we're headed toward 3. 5 from the right, we're headed toward 3. Therefore, the limit as x approaches 5 is 3, and f of 5 is undefined. Okay? I'm betting you can do 3, 4, and 5 on your own. So hit pause on your screen, do 3, 4, and 5, come back, and they'll be magically here. All right, so welcome back. Hopefully you paused. So if we come down here to example 3, as you come from the left, you get to 4. As you come from the right, you get to 5. Therefore, the limit does not exist, but the function value equals 4, because at 2, you have a y value of 4. Next one's a little bit more interesting, and to be honest, the limit as x approaches 8 from the left and 8 from the right is kind of a guess, but it's an educated guess. So if we come at 8 from the left, we're going from like 4-ish to 78 to 150. I would lean towards saying that coming from the left, we're headed toward positive infinity. That's getting pretty big pretty fast. And then as I come at 8 from the right, I'm going -3, -400, -700. That's headed toward negative infinity. Therefore, my limit does not exist, and the function value is undefined because it says so. And then last but not least on the bottom here, what I wanted to bring up down here is if I come at 11 from the left, I'm going from 0.01 to negative 0.001 to 0.001. Does it matter that I'm going from a positive to a negative back to a positive? No, it does not, because these values are still getting closer to 0. Same thing on the right. Even though it goes negative, positive, negative, that's not a typo. It's still headed towards 0. So therefore, the limit's value is 0 and the function value is 0 because it says so. All right, so there's the easy stuff. The back is the hard new stuff, which you have not seen before. So these are what I like to call special trigonometric limits. So if I want to evaluate the following limit by looking at a graph and looking at the table on your calculator, I want you to get out your calculator, graph this right now. I'm going to do the same. All right, so I have my calculator out. I'm going to make sure that I am in radians because when you are doing calculus, you need to be in radians. And then I'm going to graph sine x divided by x. And get rid of the rest of that stuff. It looks like I have an extra parenthesis, though. So I want to look at the graph in the table, and I want to look at the limit as x approaches 0. So when I change my window here, I'm going to make my x window just go from -1 to 1, because all I'm interested in is what happens when x equals 0. The rest of it, I don't even care. So sine x divided by x, well, the highest sine x can be is 1. And then I'm dividing by x, so let's see. Near 0, this is positive, so I'm going to go from like -2 to, I don't know, let's say 3. And I'm going to hit graph. And here's the graph of sine x over x near x equals 0. So the graph looks like this. I know that's cool, isn't it? And now I want to look at the table. So before I look at the table, I'm going to again start my table at, let's say, 0, because that's what I'm interested in, and do a delta table of like 0.01, so that when I go to my table, I can scroll up a bit so I can see to the left and to the right, and I can look at my table values. I don't know why that won't go away. So anyways, if we look at this graph in this table, where's the graph going as x approaches 0? Well, as x approaches 0, sure to me looks like the graph is going to y equals 1. And if I look at the table, those y values are going to 1. So I would say the limit as x approaches 0 of sine x over x is 1. And I would be correct. So then, let me try and make that disappear. There, come on, there we go. So we have that. Okay, fine. I don't really know why that's happening, but it seems to be appropriate. Now I'm going to come down here, and I'm going to look at the graph in the table for 1 minus cosine x over x. And if I do that same thing, and I come back to y equals, you do the same as I am. So if I do 1 minus cosine x divided by x, and I graph that one. Here's the graph. Seems to go through 0. I'm comfortable with that. And then if I look at the table, again, that also seems to go to 0. So to me, it sure looks like this limit equals 0 and the other limit equals 1. And again, I'm pretty comfortable with that. The graph in the table seemed to support it. So if I come over here, the limit of 1 minus cosine x over x is 0. Now, why are these special? Why do we look at them? Well, the reason we look at them is this. If I were to just plug in the number, if I were to just plug in 0, I get the sine of 0 over 0, which is 0 over 0. And I've told you before that when you get 0 over 0, that means that something's probably happening that's the same on the top and the bottom, and maybe you can cancel it out. Well, I can't cancel here, but it is true that the same type of thing is happening at the top and on the bottom. If I were to graph y equals sine x and y equals x and look at them near 0, they look something like this. Y equals sine x near 0 does something like that, and y equals x near 0 does something like this. They're really similar near the origin. If I were to zoom in, ooh, I can show you some magic here. If I were to zoom in on my little graph thing here, obviously it's not drawn to scale, but it's good enough. If I were to zoom in right here, nope, I wanted that to be a square. Nope, doesn't want to. Anyways, if I were to zoom in on that point, you would see that they're pretty similar. That means their quotient is going to be the same. Therefore, our rule is the limit of sine x over x is actually equal to, why won't my pen show up? Is actually equal to 1, and 1 minus cosine x over x is actually equal to 0. There's my pen. So this is 1, this is 0. Sorry for the little computer snafu there. All right, well, what happens if I want the sine of 3x over 3x? Well, here's a little thing we're going to do. I'm going to say, you know what? I'm going to let y equal 3x. So when I go to write this limit, I'm going to take the limit of sine y over y. All right, let y equals 3x, so sine y over y. And if x is approaching 0, then y would be approaching 0. Therefore, this limit and this limit are equivalent. And what did we say the limit as x approaches 0 of sine x over x was? Well, it was 1. It would still be 1 even if I wrote it as y instead. So that's a 1. Well, what if it said 5x over 3x? What do I do then? Well, here's what I can do now. I'm going to take this. I'm going to multiply the top and the bottom by 5. So this is now 5 sine 5x over 3 times 5x. Now I did a little commutative property here, but I hope you think they're equivalent. 5 sine phi x, 5x, 15x on the bottom. And this is the same as 5/3 times sine 5x over 5x. So if I then take the limit as x approaches 0 of 5/3 times the sine of 5x over 5x, for the same reason we had above, if these things match, this limit goes to 1. And the limit as x approaches 0 of 5/3 times 1 would just be 5/3. Well, there's got to be a rule there. There is a rule for that. For all of these reasons, for all this work I did, all you really need to remember is that assuming x is headed towards 0, the sign of ax over bx, that limit is going to go to a over b. Because every time you can make the angle part match the bottom with a little bit of coefficient tricks. All right, when I come over to here, tan 3x over 3x, well, we didn't talk about tangent. That's okay. Remember, tangent can be rewritten, as sine over cosine. So I can rewrite this as the limit as x approaches 0 of sine 3x over 3x cosine 3x. It's going to be the same thing. So I can also rewrite it as the limit as x approaches 0 of sine 3x over 3x, here's the things that match, times 1 over cosine 3x. And we said if x goes to 0 and the top and the bottom match, that part goes to 1. And as x approaches 0, this is going to be 1 over cosine 0. Cosine 0 is 1. So this limit equals 1 as well. Because of all this stuff I did, tangent also has a rule. The rule for tangent as x approaches 0 is since tan is just like sine over cos, and cos at 0 goes to 1 anyway, tan ax over bx also goes to a over b. All right, so what do I do if I have both? If I have sine 5x over tan 2x, I'm running out of space. Hopefully you're not. I'm going to put this stuff down here. I'm going to rewrite this as the limit as x approaches 0 of sine 5x over 1 times, well, tan 2x is sine 2x over cos 2x, but it's on the bottom, so I'm going to keep switch flip and write it as cos 2x over sine 2x. So then, oh, sorry about that. So then I'm going to look at this and say, all right, what do I do now? Well, here's what I'm going to do. I'm going to rewrite it as sine 5x over 1 times 1 over sine 2x, where'd my n go, times cosine 2x. Okay. Then, this is supposed to have an x on the bottom. It doesn't have one yet. You know what? I'll put one there. I'm going to multiply the top and the bottom here by, let's say, 5x. I don't need the 5x in this fraction, so I'm going to be a little bit creative. This 5x is going to end up here when I write it a second time. And this 5x is going to go there. It's multiplication. I'm not distributing. I'm just saying that sine 5x times that, I can rearrange. So I have the limit as x approaches 0 of sine 5x over 5x. Again, this one came from that. Times 5x over sine 2x times cosine 2x. So as x approaches 0, this guy goes to 1. Well, wait, what did I tell you to do if they're upside down? I didn't. Well, you know what? If it's upside down, you just write it upside down. You just write it as 5 halves. Reason being, if sine x over x goes to 1, then x over sine x still goes to 1. Because if you flip upside down, 1 upside down, it stays the same. So this guy's going to go to 5 halves, and then the cosine of 0 is 1. So this, when I multiply them all together, becomes 5 halves. Oops, I didn't write 5 halves there. Sorry, this is 5 halves. Sorry about that mistake there. Therefore, if you have sine ax over bx, look what happened. When I come back to here, this was really sine 5x over sine 2x, and I got 5 halves. So if you have sine over sine or sine over something with an x, rule stays the same. You just take the ratio of the coefficients. All right? I want you to try these next two and see what you can do with it by rearranging it and trying to remake it as sine ax over bx. Come right back and we'll stop this. All right, almost done. So if you look at this one right here, sine squared x. Well, sine squared x is sine x times itself. So I can rewrite this as sine x over 2x times sine x over 1. Sine x over 2x goes to a half. Sine x, as x goes to 0, is 0. 1 half times 0 is 0. Then if you have sine x over x squared, same idea, except you have a duplicate on the bottom. Sine x over x goes to 1, but 1 over x at 0 is undefined. 1 times undefined doesn't matter. Undefined trumps it all. So I said this video was going to be 10 minutes. I'm sorry, it's 15. Hopefully you got everything out of it. We will talk about this tomorrow. But long story short, you just need to know the shortcuts, okay? And then you should be all set. See you soon.